Now here the creep testing and analysis. Okay, so to predict the creep behavior and material life, engineers perform the creep test at a elevated temperatures using the constant load or stress. So how we do the testings? We do the testing at a constant loading. Constant loading, why? Because suppose in a practical life they are going to have a experiencing of a, suppose 100 Newton. So what we do the 120 Newtons for a, I mean, constant. Because if we have kept, or we can say 150, so that, and that would be the constant. But in real life you must be having the less temperature as we are taking the test. Suppose we are taking test at a 400 Kelvin. So we are sure that our real practical life application would be like 300 Kelvin. So you have kept the constant, loading, but in real life, the loading would be fluctuating, right? Your loading would not be exactly right. Sometimes you would be high, little bit, or you would be having low. Okay, so low is not going to, defect your materials, but high can cause your materials or your components. For that, what we have done, we are just keeping the temperature high, though it would be not as much as we are taking testing. It would be always less than that. Okay, so that's why we keep the we keep the loading constant. The first one is the keep test setup. How we do the setup? The specimen is subjected to a constant load at the high temperature. That is very obvious. Okay, strain versus time is recorded. Okay, so strain versus time that we record. Okay, test duration can range from few hours to the years. It depends what kind of the material that we are going to test. That will decide your duration, time duration of your testing. Okay, that's why here is written the few hours to the years. Sometimes we spend years of years, so that we can check the material behavior or their keep natures. Creep rate equations. What are the equations that is going to used for the creep rate? This is the equations, and the study state creep rate, which is the main part that we have to focus. I already made you know there are the three kind of the creep stages in which in which what is the most concern stages is the second stage that we have to look into that, because that is the steady state creep. Okay, so steady state creep strain rate. This the epsilon. This one is the epsilon, or it is the strain rate basically. It indicating the strain rate is often modeled with using the empirical equation. Empirical equations. What the kind of the empirical equation? The Newton's law, which that's why it is known as Power's law. Okay, power of creep. I have already shown you in the last slide. So what is the equation? The strain rate. This one is the strain rate. Okay. So strain rate is equal to A times sigma to the power n multiplication E. E is just exponential of minus Q divided by RT. This is the equations, and it is known as the what equation? It is known as empirical equation and given by Newton's. That's why it is written as Newton's law of empirical equations. Okay. And what is E? E epsilon dot. What is under dot? Wherever you see the dot at the top, it means they are just having the rate. Okay. Dot indicates that if you have seen m dot means the mass rate. Okay. So a steady state creep rate is known as is just indicating the epsilon dot. Okay. If we talk about the what is A is the material constant. Okay. It will depend over the material. We talk about the sigma. The sigma is just applied stress, means you have applied the load, and due to that loading, what stress that material is having. Okay, that is known as applied stress. We talk about the what is the n. N is the stress exponent. Okay, if we talk about the Q, then it is the activation energy of for the creep. So what the energy that is required to initiate the creep? Okay, so creep, I mean, it will not initiate at the early. I mean, everything happen every time kind of the deformation occurs when they're taking the energy. How you can say that is taking the energy when we try to pull a material. It means we are investing our energy. That energy is basically going to stored inside the material, and that storing energy will sustain up to some limit. But for if that limit extended, then the material will start deforming. Okay. So I mean, how long this activation energy means how much energy that a material can sustain before creep. Okay. And you can say just at the energy level where the creep starts. Okay. R is like just a gas constant. We know what's the gas constant by the ideal gas equations. Okay. And we can have a characteristic gas constant or universal gas constant. Universal gas constant where we have our gas constant for the all the gases which is equal, but for the characteristics gas constant we have a different gas constant for the different materials. Okay, so T is just absolute temperature in Kelvin. So what the scale that we have to use throughout the creep, which is the Kelvin. Okay, higher temperature and stress increases the creep rate exponentially. You can see here we have taken E value. Here it is E, right? E, right? E is just exponent. It means they are increasing very rapidly. If you know what is what is the value, then you can just put the value of e to the power 2, e to the power 3. Then you can see how their value is changing. Okay, so if something is exponentially increasing or decreasing, that would be have a very sharp nature. Okay, so high temperature and stress increases the creep rate exponentially.